Oh, the audio is going to go through this. Hide the controls. I have to run. That thing's running. So everything's running here. So it's good. All right, I just have to have this on. It should show up. All right, so I wanted to go through the machine learning stuff. So, and then the homework will be on that this week. Last time I went through that there's this business analytics thing at UC that's basically kind of artificial intelligence, machine learning, Internet of Things kind of program, for business. It's actually the second best in the country. So, and it's pretty hot field. So anyway, so it's kind of something to think about or look at. And then there's a ton of money in machine learning. Let's see. Let's see. All right, now it's doing this weird projection thing, so I can't see what I'm doing. Oh, how do you turn that off? Let me just fix this. Oops, no. Why did I go into this mode? Oh, that's better. All right, because I'm in slideshow, I guess. All right, and then last time, I think I got up to, what did I get up to? So yeah, I showed you these things last time. It's like the scikit-learn. So there's ways to learn machine learning. Like there's, and then these are like all Python-based machine learning and artificial intelligence programs. So I kind of went through those last time. Oops. So this scikit-learn. So each of these will be like specific tasks that you want to do within machine learning. So the homework will be like one example where he's got it kind of worked out using scikit-learn and using Google Colabs in a web browser. So you can just kind of run this thing on a data set that he generated using block copolymers to protect native proteins in a like a device, a sensor device, So anyway, so we'll do that on Friday. I'll go through that. Anyway, so there's let me just go back here. So there's a lot of kind of papers on this topic. One that looked good, this review paper by Sue on making dielectric polymers. This is going to be for like supercapacitors or basically also memory storage devices use these kind of things. So it's going to be like some kind of active inorganic, like a metal or an oxide, and then doped into a polymer. And the polymer is a matrix to hold the materials, right? So anyway, so it's this a lot. So every application of machine learning, artificial intelligence is going to be like some kind of involved field. So this is a little bit of an involved field, right? In other words, so basically the idea is you need to get data, right? So you're going to have some kind of let's see if I can find this thing. So you need a data set, like a huge data set, thousands of data to feed into this, so that you can make the computer kind of understand some system, like you input certain things, like you're going to do a compounding of a polymer in a dielectric material. That's going to end up with some properties like the dielectric constant and the breakdown. It's basically if you put, so a dielectric is going to go into a capacitor, you have two plates. The dielectric is going to kind of store the charge. So you put a high voltage on it, it's going to store the charge. And then basically you put too much voltage on it, you reach the breakdown voltage and it arcs across it. Then you blow the capacitor, right? So you need to know like for thousands of polymers and thousands of different dielectric materials you're going to put into it at different compositions. Then also can be block copolymers and phase separated polymers, right? So there's an infinite number of possibilities for the input into it. And the output's going to be like how much charge can it store and for how long, and then what's the breakdown voltage on the thing. So that's kind of basically be what the output of this thing is, right? So somehow you want to be able to take every possible piece of information that you can get, then feed it into this, then have the computer link those dots of information and weight the ones that are important by an iterative procedure to get the result that you want to see. Like what's the output of it? Okay, so basically this kind of process is how everyone's going to interact with this when you go to work at a company, or if you do research, like every one of you will have this, and this is going to become like more and more and more important. So right now it's been around like 10 years, maybe 15. And then, so it's just at the beginning is something that's going to kind of explode. And then what's going to happen is, so instead of like having a DSC to measure the glass transition and the melting point of your polymer, you're going to have some way to make like an array where you can sample every possible combination of any possible polymer. Okay, to do that, automated synthesis machines exist. So you can like, for instance, in the paper we'll look at, they have an automated block copolymer, so we can make 2,000 samples in this in like a day or a couple of days. So in their small samples, so he feeds in all the monomers that you can put in. Then every block copolymer is going to have like the A and the B block. There's going to be like how much A, how much B, and then you can do tri blocks, etc. So you can program the machine with all the input of the monomers to spit out like a huge array of different polymers, with different functionality that can, in that case, is going to be to interact with a protein, right? So protein has a certain surface on it. It's got certain functional groups pointing in different directions. The block copolymer is going to kind of wrap around it. And if it fits just right, then it'll be functional. If it doesn't, it won't. Right. So every case, like the dielectric, yeah.
What is the fourth step? I can't see because of the.
Oh yeah. What is the fourth step? Let's see, I can get rid of this. Oh yeah, yeah. It's properties. Yeah. Yeah, all right. I didn't remember what it was, but so it's basically, yeah, the input data. So the problem with the data is that it's going to be from, all right, so you can go online, search papers, right? But you need to have like thousands of papers and everyone kind of puts the numbers in different ways. So there's programs that actually do like data mining from the internet, like go fishing for data, right? So then, but you don't know like the accuracy of the data, like can you believe it or not, right? So the machine doesn't have any way to tell, so it'll just take anything you put in, and it could be that. So there's a lot of problems you could run into. So basically, in this case, when they're doing this dielectric thing, it's absolutely a total mess. Like you can't trust anyone's data. It's all like totally different units and things, and different machines used to measure it, right? So basically, they go back and say like, well, and this is a common way to do. Well, you run a simulation program so they can simulate these dielectric materials and certain aspects of them, especially like the interface between the inorganic and the organic is an important aspect to this, because that's where the charge kind of builds up. So that's where you're storing charge, basically at the interface. So you can use this phase field simulation to simulate the interface between the inorganic, organic. He uses molecular dynamics to simulate the polymers, and then density functional theory to talk about the band gaps and things of the inorganic in it. So it's like three completely different fields of simulation. Like these people wouldn't normally talk to each other, right? But from those simulations, you can generate kind of fake data, that you can feed into the program. Then the output of that is going to be which of these things that you spit in are going to relate back to like the capacity of the composite that you make, or the breakdown voltage, right? So there's this whole set of data. Somehow you have to kind of somehow weight those and get a result out of it. So this kind of box part of it is packaged. That's what these these programs will do. Like these Python script kind of language operators will do. Like if you have data, like image data, and you want to classify it, which one has a bicycle in it, there's a classification subset. So you can click that and get into Python code. Python packages you can load into your computer and run as scripts. So basically, you're going to just be writing uh, pre-formatted commands with pre-formatted arguments where you put in the numbers and then it does all the work, and you kind of trust the people that made the Python package that this is going to do the thing that you want, like predict something out of it, right? And the thing that you predict, so the thing you put in, so you have to take your data and then turn it into ones and zeros, basically. So you have the dielectric constant for the material, and gonna have to turn that into something like a 0 to 1 range. And then, so you're gonna have a conversion of the data that you get into some format. Then you're gonna have a weighting factor in front of that. So you could either sum all the parameters together with their weighting factors, or you could have some other formula to do that, right? One formula would be, say you took two numbers and you did like a correlation function between them, like we did before, like with the thing you do time one, time two, multiply them together, and then divide by the average, and you get a number from that, which would be like a correlation function, go from 1 to 0, right? So basically you can correlate any two parameters like that. So that's one approach. One approach is just weight everything summed together. Another approach would be like polynomial, like say you're gonna have a polynomial series for every input parameter, then end up with your resulting features. And then you could do this correlation function approach. And then, so it goes on and on. Like, in other words, this could be an entire degree in a sense, but some way you have to figure out how to interact with this thing, right? So because this is going to be like, you're going to be thrown, someone will throw this at you. Let's say, this is how we're going to do this stuff from now on. We're not going to do like, you're not going to sit there, get the data and then think about what the problem is. You're just going to feed it all into this computer. It's going to spit out the answer, right? So anyway, so it kind of works and kind of doesn't work sometimes, like I said the last time. But so basically that's the scheme of how these things are going to go. Anyway, so this is a nice for this problem. So he has to use both data that he collects and also the synthesized data that he makes. He's feeding, and then you need, because he has a polymer and he has the inorganic. Inorganic's pretty easy. It's just the chemical formula, right? And maybe the crystal structure that it has, or it's amorphous. In this case, the amorphous things have better dielectric properties than the crystalline for these kind of composites. Polymers are like a huge mess though, because you can have branches, they can have different topologies, you can have different molecular weights, you can have multiple components in it, different functional groups, so that there isn't really a common way to talk about a polymer that you can feed into a computer. In other words, a computer has to be like 1, 0, 1, 0. And this is like a chemical structure. So it's not fitting into that picture very well. So people spend a lot of time figuring out how to fingerprint. They call it fingerprinting the polymer. So basically you can turn that structure into like a code, right? So basically you can feed all the possibilities of producing the polymer. So you'll label your data with these fingerprints of what the polymer was that went into it, and also the fingerprint of what the inorganic component is, and the fingerprint of the composite, and maybe a fingerprint of the structure, like what's the structure arrangement of the chemical components that went in. So all that information. So a lot of the work is like figuring out how to do that front end. I would, in order to get it in a format that these engines can eat. Like you have to turn it into food for the engine, meaning ones and zeros, right? So basically there's some way to do this. I mean, in other words, there's all kinds of algorithms. And again, there's like programs that will do this for you. So it's like you have to kind of fish around and figure out which program is going to work for you. It's like classification, clustering. So these things will take huge data sets and minimize them into numbers that can be fed into a machine learning package. So anyway, and then the output of this is going to be whatever you want. In other words, the dielectric electric breakdown, permittivity. So each capacitor is going to have a mass, and it's going to have the energy that's stored in it like a battery. So there's a specific energy per mass or per volume, depending on what you're interested in. Right. And again, like the capacitors mentioned before are going to be for short-term energy storage. It's like if it gets cloudy out and the solar panels are shut off, then you have a capacitor there that can last like 20 minutes. It'll store the energy up so you get a continuous output from the thing. It's a lot cheaper than a battery. There's no electrochemical, nothing going on. It's just a static thing that stores a charge. So, but these can, you can build a supercapacitor that can last like a day. Right, so it can be almost, then you can, other alternative would be like a flywheel or something that would store energy, right? So, other than batteries, right? So this is like a cheap alternative, and it's also better for like short term, because batteries, if you cycle batteries a lot, then they wear out. But cycling a capacitor, nothing happens. It's basically, if you have something like, oh, you need to store up the energy for the flash bulb on a camera, use a capacitor, right? Because the battery, if you had to charge, discharge, and rapid discharge all the time, eventually it breaks down. But the capacitor will last forever, right? So
Capacitor is
it's
a
two
one-time
plates.
discharge, right?
Yeah, well, no, it's just exactly the same as a battery. I mean, a battery is a one charge discharge too. I mean, once it's out, right? So they're the same thing in a sense. From an electrical perspective, they're the same thing. One is better for short term, the other is better for long term. But basically, there's a significant overlap between the two, right? There's this kind of range of overlap between the two. And then the capacitance, the time storage of capacitance is improving every year. And that's why they're doing this polymer dielectric thing, because this is a lot cheaper way to go than batteries, especially if you have this constant fluctuation in some input thing. Like for a day, if you need to go overnight with the solar panels, a battery's better. But if it's clouds coming on the way, this is going to be better. So that's kind of where it is right now. But that it'll change like this. That's what this research is trying to do. But it's like the superconductor, room temperature superconductors. It's like an infinite number of components you could throw into a metal oxide. Any kind of things, and there's a lot of things people haven't thought about. So if you could write a program that could throw all those things in and then predict from what's known about metal oxide mixtures with as far as their superconductivity temperature, then supposedly this thing can figure out what the best mix is. So if it's kind of a compounding problem, which is like what most people are doing, don't you're going to make something, you have to figure out how to compound it. It's skin cream, whatever, anything, right? So basically this looks pretty good, especially to business people versus hiring like a whole research division that's going to do the same thing. And here, so right now, the data you get, if you get it off the internet from papers, is free. So you don't have to pay anything for it. I mean, so there's debate over this, like who owns what. This is like legal debates over what you own when you produce something. And then like if it's used to do something else and a computer generates it, don't you own a piece of it, of what comes out? So there's some things like patenting the output of this is going to be a little bit difficult. There's going to be some arguments over who owns it. But if it's just making, frosted flakes or something, and like which is the best sugar source to put into it, whatever, then no one's going to really argue about it, I guess. Right. So basically there is some debate over like what, anyway, so you end up with properties. Then once you, and then it can also predict like what would be the best thing to do it. So if it predicts what's the best thing to do it, that's the inverse design. Then you make that thing, then you feed that data back into the thing. So this is a loop of the computer tells you what to do, you do it, and then feed it back in, and that helps the computer. Or this whole operation down here is another computer. Like in other words, the synthetic scheme with the automated synthesis is going to be like, it has all, so there's just a lab technician that fills the vats with whatever the monomers are. The computer runs the reactions. They're on really small scales. There's no waste. And they just have these little like microgram samples that feed into whatever analytic equipment, all done with robots. I mean, exists, this is not the future, but so this exists. And people are doing this to do things like drug development, like where there's a high value added product. I mean, they're doing it already, but you'll see it's going to eat into every field. Like it isn't going to be just high value added in the end. So it'll be just how you do things, and the cost of the equipment to do this is going to drop. So basically knowing about this is going to be some advantage. Unfortunately, I don't know that much about it. I know some about it, but not as much as you need to know. Basically, you need a course in this, at least, maybe a degree at some point, to how this works out. And people that are working in this, so people put blinders on, they get stuck in their field, then they just do this stuff, right? So there's a lot of things like stupid things being done with this, like things that could have been done better some other way. but just doing it to write a paper or get a funding for something, right? So I'll show you, there's a whole slew of examples on the web page of how this thing works. Anyway, so there's a lot of, so if you like statistics, which nobody does, and this is basically like your heaven, you know, because it's all statistics. It's all going to be like these regression analysis, and then you have a data set. So you feed in these data points. It does some kind of minimization. It comes up with like the blue curve or the red curve. It predicts like some point. You measure that point. It isn't in the right place. Then it improves on the regression of the thing. Then finally you get a thing that fits the data. So it's kind of like an iterative process of, so the function that's fitting the data isn't based on any theory, like any science or anything. It's just some statistical function. It could be a polynomial, could be based on correlation functions between the points. And this is an XY plot, but it's going to be Y. So it's going to be 10 Ys and 50 X's. Right? There's going to be like 50 input, maybe 100 input parameters. There's going to be 50 output parameters, and you're trying to optimize over this multi-dimensional space. So you can't exactly show it in a graph. Right? So it's trying to do this kind of process in multi-dimensional space. Right? So it's being done, you know, so it isn't something that's not possible. There's an awful lot of terms like this. So surrogate model means empirical, means just guessing. Model means like you have a theory that's going to go behind it and you predict. Surrogate model means it's a free-for-all, like you're just doing anything. It's just maybe summed together with weighting factors, polynomial, or the computer can try every possible combination. See, it's not a person. It can do the sum of them with weighting factors in a couple seconds, or maybe less than a second. Then it can do the polynomial. So you'll see in the routine for the homework. So he does that. He feeds it into all like 5 different regression processes. Then you just push a button, and this is all prepackaged. So you just say, I want to do binomial, whatever, this and that and that. And then you just push a button, and then you wait. You actually have to wait like 15 minutes. Then it tells you which one was the best one. What's the answer? It spits out the whole thing, right? And tells you what if you had chosen that one, what would the answer be? So basically, this stuff is all prepackaged. You just need to kind of know roughly what the words mean a little bit. But there's a whole lot of words, and they keep getting more words every day, basically. You know, so there's more and more of these kind of statistical, like surrogate models, a general word, but so evolutionary. So the ES, he calls it in the papers, evolution searching is something that's roughly based on DNA and chromosomes, and how you can, if you combine 2 answers, and then you get a third answer out of that. So it's kind of like an evolution of a process, you know. So then generative model is kind of the same thing as evolution searching. It's like basically it's modeled on biology in a loose sense, you know, and the idea that you can have like two things match up and then produce a third thing, and the regressive and the dominant features of the 2 things. Anyway, so these things are all prepackaged, so you don't necessarily need to know how to do these things. So those are all similar to each other, like genome approach, evolution searching, generative model are all kind of similar to each other in some sense, you know. This identification thing. So, all right, so kernel regression is going to be this idea of like correlation function versus a weighted sum. You're going to say like these 2 points, if I multiply them together, take the average, then I get a probability from that, like just like a correlation. But it could be like multi-dimensional. So you have 20 things that you're looking at in various binary or higher groupings of those to get the correlation between all the parameters that you're putting in, right? So anyway, so anyway, these are just terms that are kind of used in this field, right? Let's see. They talk a lot about this, but this is just like kind of like a least squares routine, you know, in a sense. This correlation coefficient, you end up with like 0 to 1 kind of how things correlate with each other. In other words, the answer, the thing you want and the thing you put in, how close do they come out from each other? It's going to be this correlation coefficient. Like how does the property that you get out compared to your desired one? There's going to be some kind of correlation. Anyway, so in terms of the other thing is that this field's changing quickly and there's a lot of flim-flam in it. So in this paper, which I think was 2020, maybe like 4 years ago, he lists like these sources for polymer. Like if you wanted to find TG of polymers or melting point, the surface tension, like all the parameters are listed. So there's different groups that have compiled all that information. It's like that'll be at some point valuable. So this right now isn't commercial. These are all funded by the government, basically. So Polyinfo is the Japanese government. This Crow thing is US. So a lot of these are US. NIST is US. Polymer Genome's US. So a lot of this is like US stuff. There's also Japanese and European sources. So if you go there, see if this will go there. So this is that link. So basically this data in here, in order to access it, I think you need to, let's see. I don't remember exactly how you access this, but basically, so you can see this polymer data in here and you can search it. Basically, so if you're writing the machine, so this will also output it into a format that can be imported into those programs. So it has to be in the right format. You don't want to have to manually kind of fix it. Or you can write a program to fix things, but basically, this comes out already in the format that you need for those programs. Let's see.
That is the training data set.
Yeah, those are the training data sets. So no, so you get, all right, so you're going to have a training data set, but from that, you're going to have a huge data set. And you're going to pick out the training from within that, and you're going to separate out like what you want to predict. See, from the same data set, you're going to have you're going to cut it A, B sections, B is going to be smaller than A, and A is going to be the majority. And then you're going to see after you learn from the A, can you predict B? And then, so it's still known, everything's known. And with that way you can kind of see if your program's working right. And then you can go to like, I want this property, like something different from any of the training set and see if it can predict it. And then when you get that, then you make the stuff and feed it back in and see if it worked. And if it didn't work, it modifies the program and it predicts another one. So you make that one. So that's kind of the scheme of how this works.
Tell it that it didn't work. Is that what?
Yeah, that's exactly what it is. Yeah, that's what inverse design is. And it feeds back into it. And then it can kind of come back and give you a better answer. This is my understanding of it. I have to quote that in as a qualifier because it is like a field to itself, and I'm not in that field, but it's better. Like, I think you guys are all going to be in that field. Like, I don't think you're going to be able to avoid it, So, and it also, I guess it's kind of exciting. The people who are working this are really psyched about it. Like, they're really excited, but they also like they're just in that field and they don't see that, like, they don't see the whole picture of it, right? So, that's Polyinfo. So NIST is a big place for this because they're based on like, I forget what they're supposed to exist for. Something to do with industry. So basically, they were National Bureau of Standards. They were standardizing everything like weights, temperature, whatever. And then they grew into National Institute of Technology, Standards and Technology. So they broadened out into like, what kind of technology do you need to function as a country? That's the kind of, so that's something like NIH for science, but they're much smaller. Right? So anyway, so they are doing a lot of this database. So they've been doing that for probably 20, maybe more years, like putting online all the information about every material on Earth, and basically giving the best numbers you can get. But they have, so within that, it's called the NIST web book, has information about everything. You can Google if you need to know the IR spectra for PET or something, you can just find it there, or NMR spectra or the glass transition, anything of any kind of polymer or whatever, right? So, and also they sell standards. You can buy a standard whatever and just get it from them. It's already been fully characterized, right? So So that's, so there, it actually falls into their realm pretty well, this stuff. So, and they, so you can find on their thing like data if you need it for polymers. And then polymer genome in this, so this Crow thing, so like 2 years ago, this Crow thing was an active web page. You go to look for Crow now, it's a dead link. And there isn't any Crow. So basically, this is like a grants run like 3 years. And they're just like once a grant runs out, then the Crow disappears. So far, this isn't like a consistent thing. And the same with polymer genome is kind of fallen apart. Like it was hyped up a lot. There were talks at meetings, there were articles written in Nature and stuff. And like now, I think polymer genome link is also a dead link. So basically, because it's kind of a growing and kind of nutty field, things are showing up and then flim flam get the money and leave, and then nothing's left of it. NIST is a reliable, permanent source, though. And this Japanese thing seems to be permanent. So basically, you might want to pick and choose where you're getting information from things. I mean, if you go in, like search for Crow, and then people are complaining like they were using it, and then it disappeared, you know. So anyway, so that's an issue here too. But anyway, in this paper, he's using there's polymer data sets for polymer dielectrics that he's using this QM9 and something else. So basically, in this review paper for dielectrics, that's the things he's using. Then everyone's like nano minus for nano materials. This is at a Duke thing, you know. So anyway, so this in that dielectric paper he shows this is kind of useful, I guess. But basically, like if you need information from simulations to augment the data from the papers and from the internet, and these are the different. So he does all these in that paper, all these simulations, right? So he's going to simulate band gap, the trap states or something for non-conductors can trap the charge at the interface, and that's kind of how a dielectric's going to operate. You can predict that with like density functional theory or quantum mechanics simulations, right? So again, like each of these is a specialized field, and so people don't usually do all these simulations, like from quantum mechanics to finite element. Basically, in this paper, he does, right? So that, and these are packages. So it turns out the quantum mechanics simulations, you have to buy the software, it's expensive, right? Molecular dynamics, it's mostly shareware. So basically, you can freely do that. And phase field is kind of a specialized for this topic, like basically dielectrics, like what's the interfacial breakdown electric field type thing. And then finite element is a commercial. Those are also commercial. That's a large scale simulations of kind of bulk objects using kind of a grid operation, right? So anyway, so it's nice that he shows this, and he shows like these are, so there's different time scales and size scales. So these things are all really short times, and these are really long times. So in order to get the data that you need, in other words, there's different instruments that also measure these things. Like a DSC gets the glass transition, she calls transmission here. And then band gap, you can measure with spectroscopy. And then these things you can measure with electronic measurements. And then, so there's basically different techniques to measure. So these are published data, and then you can compare with the simulated. You can feed in both into this package, right? That's the idea. So anyway, so that's the idea. Like he's going to combine both those data sets, and then he's going to identify what they are with the fingerprinting, and then feed it into this package with the properties. That's the routine. Basically, everybody's going to use. What else is in here? So SMILES is a thing developed at MIT to label the polymers. BIOVA is a similar kind of thing. In other words, breaking down the polymers into this kind of some sequence code from their topology and everything. And then this so basically this software, this RD-Kit is a Python software that you can feed in ChemDraw drawings of your molecule. then it'll spit out the SMILES code for it that would feed into the machine learning package. So it's everything's a package on a package on a package, but basically these are all just line code. Just type in the line code. You don't have to program anything. Like it's already programmed, so you just have to figure out how to run a Python script. That's it. And that's what the homework is, to do this Python script thing. Then yeah, in this I don't know what paper this is from, but basically it's the idea that so the fingerprint of whatever you put in is going to include like atomic level, and then maybe quantum mechanics if it's this dielectric thing. Then the morphology. So it's going to be like a hierarchy of fingerprint. So somehow your fingerprint has to include all this information to feed into the machine learning thing. And there's a software package to do this. This Quasar thing allows you to do that kind of packaging, making fingerprints that would feed into the other code. This is like a list of papers and what program they use, I think. Anyway, so there's a lot to this. That's the point. I mean, with these nanocomposites, so there's also like, say the nanoparticles or the particles you put in are going to have different aspect ratios. So they could be sheets, disks, spheres. They could be just aggregates. So there's a lot of, they give these three, but sphere, disk, ellipsoids, but basically they could be a lot of other things. But once they're asymmetric, then you have to worry about the orientation too. So the parameterization to feed in starts to get complicated, right? And to get that all from the literature is going to be difficult, right? Because so there are softwares that will generate data from asymmetric particles with different orientations. It'll generate like permittivity, these kind of properties out of it, right? So basically that exists. And then there's this issue of like how the things put together, like so basically he's going back to saying you have a correlation function, you can get the scattering kind of information. K would be Q, this would be the scattered intensity, and then you can predict like the two-phase structure from that somehow. None of these things are really true. Like you can't predict the two-phase structure from the correlation function, for instance. But this is a parameterized thing that could be consumed by a computer because it's a bunch of numbers, and this is an image, right? The alternative is you take the image, you just do image analysis without thinking, which is so the machine learning is really originally done just for image identification, like is there a bicycle in this picture type thing. So computers can do that. I don't know why they put it as a test of human now, because the goal of all this, a lot of this, like half the field is image identification, like to tell you a picture of you, are you type thing, so anyway, so basically you can this software just to analyze images, like it's just Python code already written that you just can feed in any number of images and get basically anything you want out of it. So the idea of using correlation functions is kind of goofy if your data is images. This is just showing in specific, yeah.
For the picture slide, this was
Mhm.
it was one of the two phases.
Oops, this, all right.
So I was wondering, so when computer calculates the image, what process does it use? Does it use the process of drawing several different lines vertically and horizontally and then counting the variation of colors, or what? Like what process does it use in those two phases?
Yeah, this is what it uses. It's going to do something like this. It's going to this is what it does for actual photographs, right? So it's going to take the photograph of a bicycle, it's going to break it into component pieces, and it's going to end up with something like that. And it's going to say, it can digitize that, like how many circles are in that. So there's 2 circles. And then how many, whatever paralleliped that is, are in that. And it can say, well, there's 1 of those. And then whatever the other things are, it can classify those. So it's going to break this apart into component parts like that. And then that becomes a digitized package. So you can say like wheels 2, so then you normalize 2 by 2. So you have wheels 1. It's 1 to 0. You need kind of 1 to 0. And it's going to weight that factor by a constant. It's variable, right? And it's going to weight each of these things that it has, like parallelipiped things, by a constant factor. Then it's going to be fed in the answer. It's a bicycle, right? And if it can get the weighting factors right, it'll come out with the answer. It's a bicycle. If it's wrong, then you go back and change the weighting parameters. So it has to have a way to decompose it into components that'll be like 1, 0. It's going to weight each one of those, and it's going to be able to identify that's a bicycle. And once it has that, okay, then you can go back and say, well, make me a bicycle. And then it can make these pieces and put it back together into a bicycle. It can work forward and backwards. This iterative weighting thing can go forward and backwards. And that's sometimes the steering wheel will be on the seat if you do that. And you'll notice in these that's how people identify if it was an artificial intelligence manufactured photograph, because there'll be like an ear on their nose or something. And it's like, it looks exactly like a human, but there's an ear on the nose. The computer didn't actually get that because that wasn't included in the learning thing, right? So there's ways to get around this, like you can see, but
I just want to make sure that's what that Smiles Python code does. It
No.
disassembles it like that.
no, smile, kind of, but for a molecule, for polymer, which could be branched, it can be block copolymer, it can have different block lengths, different molecular weight. So it could be just a protein that's got all different amino acids mixed in a random array. So Smiles will turn that into a number, like a number and letter sequence. It can be fed into the computer. So the computer doesn't care that it reassembles into a protein. I mean, it just cares that it has a number and letter sequence, that it can weight each one of those sequences with some weighting parameter and then iterate until it says that's the right thing coming out. So it's kind of like, at some point, so the computer is just taking ones and zeros. So that's why the programs are all the same. You just have these packages, because the work is to get your data into the format of 1 zeros. Once you do that, then it doesn't matter, and you answer into 1 zeros. And in between packages will work for anything. It'll work for image analysis. It'll work for like figuring out the glass transition. It'll work for the dielectric thing, because it doesn't have any idea what it's doing. All it knows is that it got the right answer or it got the wrong answer. It's going to go back and fix it until it gets the right answer. So it's like, looks like it's learning because it works so fast. It's doing this kind of stupid thing over and over and over again. And finally it looks like it's smart. Oh, it's magic. It came up with the answer. But basically it has no idea what it's doing. The computer that's the point of it. It has no idea at all what it's doing. Right. So you can feed it in something, it feeds out something. It's just feeding in and out ones and zeros. That's it. But you interpret it for the way that you did your thing, so anyway, so it's kind of interesting and a little scary, especially, so I put a thing at the end which is kind of political. Basically it's about how the Israeli, and so we develop, and the Israelis are using a way to identify targets to kill, like to send a missile in to kill somebody. And basically, so they take all this information, guy walking around, every possible information you get from a drone flying around, taking pictures of everybody. Then it figures out that guy's a terrorist. And then that code is automatically sent to a missile launch site, and they launch a missile automatically. So the computer essentially does all the deciding, right? So this is the future of everything, including like how you're potentially going to die. So the point is, stay away from a war if you can, because you have no hope. So they can track. You see it in these science fiction things where the guy goes to the border and it identifies his eyes, and then it just, whatever, they catch him, or kill him or whatever. So that's actually going on. Like, this isn't really science fiction anymore. So it's like more than just this. Like, you'll be forced to do this at work, but basically also in your life. So in your life, it's going to be like that too. And there isn't really a way to avoid that, I think. I mean, you can outlaw it in war, but they haven't really had much luck with outlawing like landmines, for instance. So basically outline isn't exactly gonna work. So you have to kind of think about it that way too, like, in other words, there's a good and a bad to it. I mean, you can get better peanut butter, but like, you might get killed by this thing. So, anyway, so, uh, anyway, so let's see. So they talk, and we'll be using a Gaussian process regression in this code too. So the way I understand it is instead of saying like, yes, no, you're on the line, there's like a gradient of range of possibilities. So it's like in this thing. So he's got like, he predicts the dash curve. So it's a range because the Gaussian probability of the blue line, in other words, the probability is broad here. You could have a lot of answers in this region, but it's narrow here, like the Gaussian distribution of the answers is going to be narrow, down to a point at some parts. So it's 0 sigma, right? So somehow this is like a way to weight answers instead of saying this is the answer. Like if you just do a regression, polynomial regression, you get that. It just says that's the answer. That's the point. If you want to predict here, that's the number. But this Gaussian regression is going to say, in this region, you're going to have like a 5% chance of actually predicting the right answer. And the possible range is going to be from here to here. Whereas over here, you have like a 99% chance of predicting the right answer. So it's just telling you that you're guessing here and not guessing there. So it says like you should get more points in that region to make the thing fit better. That's kind of the idea, I guess, more or less, the way I understand it, the Gaussian process regression, which is just an option you put into a line code, into a script for Python to make it run. You just say, I'm going to use Gaussian regression. Everyone uses it. So basically you just use it, I guess, in the end. But anyway, I wanted to just kind of go through a few examples of these are AI generated people, right? So you can't tell. There's no way, there's no ear in the nose here. So they fix that problem. But basically, there are ways to tell. If you kind of look carefully at things like this, you can start to see there's some problem with it. But these aren't people. These are just generated by taking a lot of photos of people, breaking them down into, like I said, like ellipsoids, eyebrow things, whatever, and then a weighting function for the parameters for it, spit out, is that a person or not? And then go back until you get that right, and then run it backwards and say, make me a person. And they can just spit out things like that, right? So it's way beyond what you think where things are, like this thing has progressed so fast. In fact, they talk about quantum computers, right? It's like quantum computers exist. I saw one at the APS meeting. Basically, the reason they're doing it is to do this kind of thing, to basically this kind of predictive algorithms where it spins and spins and spins to try to generate things like this at like 100,000 times faster than a supercomputer type thing. So it's way beyond, it's progressing. It's like way beyond what you think where things are, this whole field. Anyway, so simpler stuff is like, I wanted to just, so there's a bunch of things on the web page. If I can get there. Oops, wrong button. Oh, right button. Oops, okay. Sorry, I'm looking at the wrong screen. This guy. All right, so I can see this, but you can't. All right. Guess I gotta go there. Anyway, so let me just show you. I can figure out where my mouse is. So we got, all right, so there's a whole like pile of things here. Not sure why it's not duplicating, but I showed you last time the robots sorting out milk jugs at the recycle center. So let's see, if you look at, so this is tires. So they're doing predicting the composition. Tires have like 50 components in them, and then take all those components and just use tan delta. The tan delta peak at certain temperatures. You have to have it at a certain frequency range to get grip and get wear resistance. So this is a study to do that using machine learning, right? By Goodyear. let's see, this is studying how to produce ultra high molecular weight polyethylene using machine learning for the catalytic processes. There's another polyethylene one in here. Anyway, if you want, you can, I don't have time to go through these. They're pretty interesting to look at each one of these. There's a bunch of different kind of examples of, this is 40 minutes. So if you're right wing, don't watch this at all, you know. If you're kind of like middle or left wing, it's 40 minutes. If you don't have the time, don't watch it. If you're like whatever, you can watch it, you know. Basically, if you watch that, you'll be pretty scared about what's going on in the world. But anyway, if you want to put on blinders, don't look at that too, you know. So anyway, yeah, oh, and then synchrotron's another thing. So yeah, we're out of time, but basically automated measurements at a synchrotron. So you can set up, you can have a computer make the samples, make 10,000 samples, put them into trays at the site, at the synchrotron. Have the synchrotron measure those 10,000 samples, like 20 milliseconds of measurement, analyze the data and tell the computer what to make the next 10,000 samples. This is already being done, right? It's being done on a research level, right? So basically, and then map out like the property that you want to get out of that synthesis procedure. So it's kind of interesting, like how it's advancing there too. But you know, anyway, so next time I'll go through that one paper, which is a Tomasi thing here. Right. Yeah.
We're 14 or you do this.
Yes. Yeah. All right.